Let's talk about residual analysis. A residual analysis is a crucial step in evaluating the performance and validity of a regression model. It's useful in following ways. First, it helps in identifying the validation of model assumption, like checking the linearity of the model and how much the variables are independent of each other. Second, it helps in identification of model fit issues, like it helps in detecting the outliers and helps identifying the patterns in them. Third, it helps us improve the model performance. And fourth, they can be often used as a report or presentation to show that the model has been thoroughly evaluated. Let us check the first technique. So first we will be using quantile plot or QQ plot. So basically a QQ plot compares the quantiles of the residual against the quantiles of standard normal distribution. So let us see the code. So first we are importing the libraries, then we are importing the data set, and then we are doing the usual thing which we did earlier. We are splitting the training and validation set and doing the regression. So this step is similar to the earlier mentioned video. So this is the important step here in this case. Here we are calling the QQ plot from this library. Okay, and we are plotting a 45-degree line. When we run this, we will get the following plot. Let's now see the interpretation of this result. So if we see a point along the 45-degree line, this suggests that the residuals are normally distributed, which is an assumption of linear regression models. And if we have points deviating away from the line, like these points, if we have significant deviation in this case, that indicates that residuals may not be normally distributed. This means that model's assumptions are violated and the model might not be a good fit for the data. So basically, this statement says that if the values lie at the close proximity of this line, it suggests that this model will work well for this kind of data. But suppose if we have the data points which are very quite far from this 45-degree line, this would suggest that the model might not work properly. Now let us take a look at another technique, which is the standardized residual plot. To do this, first we define a standardization function. So as the function name suggests, it is defined to standardize z score, which is a variable, by subtracting the mean and dividing by the standard deviation. So first we have to obtain a z score variable, and then using this formula we can obtain the standardized value. A standardization is useful for comparing variables on different scale and for making variable dimensionless. Okay, so basically what we are achieving using this model. Okay, so let us first run the code and see the result, then we will talk about the interpretation. So these are the usual import variables. Here we are importing the data set. Here we define a small function to create the standardized function. Here we are reading the variables from data set. We are training we are performing OLS, and here we are plotting the scatter plot of these function. So if you run it, you can see in x-axis we have standardized predicted values and standardized residuals. Now let's take a look at the interpretation. Okay, so basically what we are achieving here in this case is that the scatter plot of standardized residual against standardized value is used to check key assumption of linear regression models such as homoscedasticity, which is basically the variance of residual should be constant across all levels of independent variables. If the residuals are spread equally along the horizontal axis, it suggests homoscedasticity. So basically, if the data points are scattered evenly across the plot, then it suggests it is the thing homoscedasticity. That means there isn't any clear pattern. So this is basically good for data. We don't want the data to be clustered around some specific region. Second is the linear relationship between independent and dependent variable should be non-linear. The non-linearity would manifest such as curved plot. Okay, so basically, if we have some dependence in variables, then the plots will be curved. Okay, for example, like here in this case. So basically, this would suggest some dependence of variables among each other, which we don't want. We want the independent variables. Third is the kind of similar to above, that is independence. The residuals should be independence of each other, meaning they shouldn't be any correlation. Okay. So how you will identify the problems? So as said before, if you see any systematic pattern in this plot, like a funnel shape or a curved shape pattern, this would suggest that linear regression model may not be best fit for this data, and you might need to consider some other modeling approaches. For example, if you see any of these or any similar kind of pattern, this would suggest that this model might not work for this data. You want the data points to be scattered like this figure.